All right, so this is the first of two lectures we're going to do on geometric optics. So this week we're going to mostly be focusing on reflection and refraction and images created by flat and curved mirrors. Coming up would be lenses next week, along with some optical devices, which I would define as anything that has more than one optical element. So stuff like putting two lenses together to make a telescope or a microscope. And we can get into things like how do eyeglasses work and like what kind of prescription, what kind of lens would you make for someone who's nearsighted versus farsighted. But to get to that, we're just going to spend this week talking about some of the fundamental principles of geometric optics. This is kind of fun because, as the title says, right, geometric optics. So we're going to be doing a lot of geometry. The principle of light is that it travels in straight lines unless something gets in its way. So unless it interacts with a surface in some way. So we're going to be drawing lots of straight lines and then modeling how those reflect or bend. So talking about reflection, there's really two kinds of reflection that we think about. Diffuse reflection is how we see most things in our environment, because most things in our environment don't emit their own light, right? So like a wall in your apartment doesn't emit its own light. So the way we can see that is light from another source reflects off of that object. And if you look at something in your room, you can see that object no matter where you're standing, right? The light is coming from that object radially outward in all directions. So you can see light coming off diffuse reflection no matter where you're standing. If I have a material where at the atomic level it's very flat, then I can arrive at what we call specular reflection, which is the kind of reflection we think about when we look at mirrors. So this is the idea that light coming into a surface will reflect at the same angle it comes in, with both angles being defined relative to the surface normal. So if I have light coming off an object, it reflects off of a mirror, right? That ray of light comes off at the same angle. But if what we were just talking about was the idea that light coming off of an object would come off radially outward from that object in all directions. So if I want to keep track of what light is doing to make an image in a flat mirror, right, I'm going to want to draw multiple rays. So if I draw a couple rays, they reflect off the mirror and then they arrive at my eye. So if I'm looking at a mirror, right, I'm seeing a light that is being reflected off the mirror that originally comes from some object. But if I geometrically trace those rays back to the other side of the mirror, they are diverging from a particular point. So that point where the reflected light is diverging from, we call that an image. So our brain can process those diverging rays of light and say, hey, there's something there. You know, in the same way we would be able to locate an object, right, that was placed in front of us. We could locate an image in the mirror, even though you might notice in the flat mirror that over here, right, no actual light is on that side of the mirror, right? No light is actually coming from the far side of the mirror. This is entirely a geometric construction, hence geometrical optics. So tracing that light back locates an image. The light does not physically have to pass through the image location for there to be an image. So when light comes from a geometric point where the light doesn't actually pass through, we refer to that as a virtual image. So no light actually passes through the image location. We just think about that location as being a point of divergence for the reflected rays. And the way we find this point of divergence is by just using straight edges to trace reflected rays back to their, or trace them back until we see that multiple reflected rays have converged at the same point. So we're going to be drawing a lot of ray diagrams to locate images and to kind of process some properties of images that are going to be important. So the idea behind these ray diagrams is we're always going to be drawing 3 rays. You could continue on and draw more than 3, but typically we're going to come up with some rules so we have 3 rays that are easy to draw. The reason we do 3 is that if we only do 2, if I draw 2 lines, they will definitely cross somewhere, right? So if I make a mistake and draw my rays incorrectly, and I only draw 2, they will still cross somewhere, and I'll get an answer for the image that may or may not be correct. If I draw 3 rays and I make a mistake, then all 3 of those rays might not converge at the same point, and that'll tell me that I made a mistake. So drawing 3 rays is safer and is a convincing way to demonstrate that you know where an image is, because it's hard to make a single mistake that would result in 3 rays still converging at a single point. So when we start talking about curved mirrors rather than flat mirrors, we are interested in something called a focal point. And so the focal point is connected to the question of what happens to parallel rays of light that are coming at a surface. We're interested in parallel rays of light, on one hand, just to kind of get a feel for the geometry, right? So we can understand, right, what the mirror is actually doing to parallel rays. Parallel rays of light are our way of modeling an object that's very, very far away. So if I'm thinking about an image made of something like the sun or the moon or a star, right, something very, very far away, I can imagine that light diverging from that point is so far away that by the time the light gets to me, the incoming rays are basically parallel. So that gives me this principle that the parallel rays correspond to the idea of an object that's infinitely far away. So if I use my principle that light coming into this mirror is going to reflect at the same angle that reflects at an angle equal to the angle of incidence, I can model the kind of normal to the surface by figuring out what's called the radius of curvature. So if this is a spherical mirror, then it's kind of like somebody cut a piece off of a sphere to make this mirror, right? So the radius of curvature is the distance to the center of the sphere that was before I cut this piece out of it. So the surface normal will be a line that points from the surface to the radius of curvature. And so I could measure the angle of incidence here. I could draw a ray that has the same reflected angle. I could do that for all my different rays, and I find that all of my reflected rays are going to converge at the same point. In this case, right, if the image is here, then right, the light's not going to stop at that point. It's going to continue on, right? So I'm going to have reflected light that's looking like it's diverging from that point. So if I am standing anywhere kind of to the left of the image, then I should be able to see the image, right? I'll see diverging rays of light coming from that point, and I can, my brain can interpret that in the same way it interprets light coming from an object. If I'm standing here, then I might have some trouble if I'm facing the mirror, or actually no matter what, because there's no light kind of coming from behind me. So in this case, the light coming from the mirror isn't diverging from anywhere. Those two light rays are still converging towards the image at that point. So I would not actually be able to see a clear image. It would just look like blurry light coming off the mirror if I was standing in between the image and the mirror.
Okay.
So the rule of the kind of rule is that you can see light that's diverging, that's currently diverging or parallel. If light is converging, it's not going to make a crisp image when you look at it.
Okay, and so like if we had, say, light from those blue lines, so maybe it's from something like a star very far away or something, and they're all those blue lines are converging at the focal point, right?
Mm-hmm.
So if we stood at a place that was further away from the focal point, we would see a larger image, right?
So when you say see a larger image, so we'll talk about image size in a little bit. The image is the same size no matter where you're standing, but if I'm standing further away from it, it takes up a smaller part of my field of view. So a way of thinking about that is like if you look out your window and maybe you see a car on a street, right? That car isn't smaller because you're looking at it from further away, but it takes up less of your field of view, right? Than if you were standing closer to it.
Okay. Okay. Gotcha.
And that will actually become important because that'll give us a distinction between what we consider like the size of the image and the angular size of the image, which is really relevant for things like a telescope, for example. So like if I'm looking at Jupiter through a telescope, I don't actually need my image of Jupiter to be bigger than Jupiter. Jupiter's quite big. I need it to take up more of my field of view. So I need angular size to be bigger. I don't need the image to be physically bigger than the object. So
Right. And I've read that like having a longer focal length can be beneficial in telescopes. And that's why you'll see some models like a Newtonian or something that have like a folded focal length. Like physically, why is that helpful or beneficial?
Yeah, we'll get there. We'll look at some like how we
yeah.
figure out like the magnification. Like once we've figured out like lenses, for example, we'll look at like how you find the magnification of a telescope. And yeah, it'll end up being that like the two lenses I use, I care about like the sum of their focal lengths. So the bigger that is, the better. But the limitation there is I need my two lenses to be separated by that distance. So it'd be great if I had a lens with a focal length of a mile, but then I would need a telescope that was a mile long. So it's kind of a give and take in terms of what I can really build.
Gotcha.
But yeah, super cool stuff coming up. So, all right, going back to the spherical curved mirrors, this idea that the parallel rays will converge at a specific point, right, that will give me an image, and we describe this as being an image at the focal point. So we say that parallel rays make an image at the focal point. For a spherical mirror, that focal point is a distance that's equal to half the radius of curvature from the point on the mirror. So that's an important geometrical point to keep track of when we are trying to find images from curved mirrors. And it's also important to note here that the image is not always going to be at the focal point, right? The focal point is the special case where parallel rays coming into the mirror make an image. If I have rays that are not parallel, which corresponds to rays coming from an object at a particular location, I can figure out where the image is going to be. It's not going to be at the focal point. But knowing where the focal point is will be helpful in identifying the image location. So we'll be drawing a lot of ray diagrams to figure out the image. There are a few equations that can be helpful. We have this idea of magnification, right, which tells us about the size of the object versus the size of the image. This is also going to be related to the distance to the image compared to the distance to the object. The reason why that has to be true has to do with, I think about the kind of ray coming in. Let's say I've got an image, or an object rather, over here. The image that hits the center line is going to reflect out at the same angle. So I end up, right, wherever my image is, it's going to subtend this same angle of incidence versus angle of reflection. So I'm going to have some similar triangles going on here. So the ratio of the height of the object and the height of the image is going to be the same as the ratio of the distance to the image and the distance to the object. That's also going to eventually show us that if we want to build something like a telescope, we're going to need more than one lens or more than one mirror. The other equation we can use here will help us find the image distance if we know the object distance and the focal length. So we have this 1 over the distance to the object plus 1 over the distance to the image is 1 over the focal length. Remember that if we had parallel rays, that was an object at infinity. So then in that case, we'd have 1 over the image distance just equal to 1 over the focal length, or that the focal length is where the image is. So that's kind of cool. That's kind of consistent. The mirror equation will be really helpful, but the strongest solutions to our problems are going to use both ray diagrams and the mirror equation, typically. Oh, yeah, I forgot I'd drawn myself this picture already. Right, so this is just what I was talking about in terms of the image size versus the object size and these similar triangles here. Okay, so in terms of drawing the ray diagram, we want to draw 3 rays to locate the image and figure out some properties about the image given the location of the object. And we're going to go through these in detail, but we're going to have these ideas for concave and convex mirrors, and then later on for different types of lenses as well. We could just draw 3 random rays, break out a protractor, measure some angles, but that gets really tricky, right? It requires us to have an exact shaping of the mirror, so we know exactly the shape of the mirror or the lens that we're working with drawn correctly on the page, which is tough if you can't just literally trace the lens or mirror onto the page. So rather than doing that, we're going to use some tricks that we know about the geometry to come up with some shortcuts. So we know, for example, that a ray that strikes parallel to the mirror is going to reflect through the focal point. So the reverse should be true as well, right? So if I have a ray coming in through the focal point, then I should have the same reflected angle as I have incident angle, and so the ray that comes in through the focal point will reflect out parallel, right? The geometry and the angles don't care which way the light is going along this pathway. So the first ray we can draw is going to be a ray that passes through the focal point, hits the mirror, and reflects back parallel to the center line or the optical axis. The second ray we can draw is the ray that goes in parallel, and that ray reflects back through the focal point. So now we've got 2 rays. They are crossing, right? Keep in mind, we want to keep track of where the reflected rays are crossing to locate the image. But to be confident that we've done this right, we want to have a third ray and show that it also passes through that same point. So the third ray we're going to draw is going to pass from the object through the center of curvature, or a point that's the radius of curvature away from the mirror. And this ray, if it passes through the radius, through the center of the sphere, it's going to strike perfectly normal to the curve. And so it's going to reflect exactly straight back the way that it came. So with these 3 rays drawn, then now I can identify the location of an image. So I've got 3 rays, they all pass through the same point. And so my image can be located, right? And it's going to be somewhere between the focal length and the radius of curvature. So some words about how we actually look at some properties of the object in the image. So you can see I've drawn a really simple object, right? I haven't tried to sketch out a complicated looking object, but we don't want to oversimplify it. There's 2 object properties I want to make sure I'm including in my sketch. One is the size of the object, and one is the orientation. So typically I will draw an object like a little arrow, because then the arrowhead gives me a sense of orientation, and the height of the arrow corresponds to the size of the object. So in this case, I've got an upright object, right? That's a certain height. So if I include those properties in my object, then I can read those same properties off of the image. So in this case, the image is below the optical axis. So the arrow that I draw for the image is pointing down. That tells me that the image is actually upside down in this case. I also have an image that looks distinctly smaller than the object, right? And that matches up with the ratio we're talking about, where it's also closer to the mirror. So I've got an image that's smaller than the object, closer to the mirror, and upside down. The last bit I want to ask, right? So it's upside down, it's smaller. The other thing I care about with this image is it somewhere where the light actually passes through, or is it like a virtual image like we would get in a flat mirror? And in this case, we have a real image. right? A real image being a point where the reflected light actually passes through to make the image, versus the virtual case would be if it was on the other side of the mirror. So real or virtual images, virtual images are perfectly visible, right? You see yourself in the mirror all the time. That's a virtual image. A real image is the only kind that can be projected onto a screen. So if you have a real image, it means that if I put a screen there, I could project that image onto the screen, and then I could see it, right? Someone could look at the screen and see the image. Okay, so one of the problems asked us to look at the concave spherical mirror with a known radius of curvature and put an object at a position of 10 centimeters. So when I go to set this up, right, I want to make sure I draw the mirror. I want to mark the focal point. I want to mark the radius of curvature. And I need to make sure that I put the object in roughly the right location. So the object is at 10 centimeters, which is between the focal length and the radius, and closer to the focal length than it is to the radius. So I can draw my three rays, right? The ray that goes in parallel reflects through the focal point. The ray that goes through the focal point reflects parallel. And the ray that goes through the radius of curvature, well, that one doesn't seem to actually get to the mirror. That's actually fine. So when I say through the radius of curvature, really I'm just saying that I want to draw a line that connects these 2 points, the points being the head of the object and the center of curvature. So I can draw my incoming ray connecting those 2 lines. It doesn't actually have to pass through the radius of curvature before it gets to the mirror. It just has to geometrically come from that direction. So it goes to the mirror, reflects back through the radius of curvature. I've got 3 rays, and so I can see where those 3 rays converge, and that should be the image. So I've done something here, which is I've left a mistake in here that is a pretty common one, which is you can notice that these 3 rays haven't quite all converged at the same point. It kind of looks like the image is going to be a little bit further down and to the left. Yeah, so does anyone have any thoughts about what might have gone wrong here?
It looks like the red ray was drawn too far over the mirror. I don't know.
Yeah, so actually I would have liked to probably draw it even further. So this is what I've kind of demonstrated here is a real life phenomenon called spherical aberration, which is the idea if I have a mirror that's made out of like a too large chunk of a sphere, so like an entire half sphere, say, then the rays that strike the very edges won't actually reflect back to exactly the same point. And as a result, it means the image made by a mirror like that is always going to be blurry. So drawing a spherical mirror, the temptation is to draw a really curvy one like I've drawn here. But to get the best answer, we actually kind of want to draw a really kind of flat one. We don't want to have too much curvature in this model to get the right answer. So the temptation is to draw like a really, really curvy mirror and then reflect back from the point where the ray touches our super curvy mirror. But if you draw a flatter mirror, you won't see this sort of error show up. And I find this error kind of interesting because it is a real thing. If I have a really curvy mirror, then light that strikes way out near the edges of the mirror won't actually reflect back to exactly the same point. So kind of an interesting common ray diagram drawing error that actually reflects real physics, which I think is kind of cool. Okay, so once I've drawn that diagram, I can check with my mirror equation, right? So the mirror equation tells me that the image distance should be around 40 centimeters. I always want to look at my ray diagram and sanity check that. So it does make sense that this would be 40 centimeters, right? That's further away than the radius. So compared to the other ones, right, like 12 centimeters doesn't make much sense. 6 centimeters doesn't make much sense. And I also noticed that the image in this case is definitely larger, right? Definitely larger than the object. Okay, so The next Polaroid question is, I'm taking the same mirror, but now I'm putting an object at a position of 6 centimeters, and I want to identify, right, whether the image is going to be a real image, a virtual image, an upright image, or an upside down image. So the equations don't really give you an answer here. Really, the only way to get through this is to sketch the ray diagram. So this is the ray diagram that I come up with, and this is a trickier one to draw in some ways. So the first ray is pretty doable. I draw the parallel ray, right, that comes in parallel and reflects back through the focal point. The second ray is a little bit harder to draw, right, because it's supposed to go through the focal point and then come back parallel. But if I draw a line from the object through the focal point, it never gets to the mirror. So again, this is the same kind of thing. When I say from the object through the focal point to the mirror, I just need to line up my straight edge, right, along the 2 points, which are the focal point and the top of the object. So I need to line up my straight edge that way and then draw a line from the object to the mirror along that direction. Once that line arrives at the mirror, then that ray reflects back parallel to the optical axis. For ray number 3, right, same deal, along a line connecting the radius of curvature to the object, reflects exactly back the way it came. And something I notice pretty quickly is that these 3 reflected rays don't converge anywhere. So there is no real image. So like I was saying before, having no real image is not the end of the world, right? A real image is the only kind that can be projected on the screen, but virtual images are perfectly visible, right? Any image in a flat mirror is a virtual image, for example, and we use those all the time. So to find a virtual image, what I want to do is I want to look at the reflected part of the rays, right? The part that comes back off the mirror, and trace those back behind the mirror to see what point they diverge from. So if I trace these back, I see that they diverge from this point here. So that's going to be my image, right? It's a virtual image because the rays are not physically crossing anywhere. And it's definitely a larger image than the object. It's also going to be right side up. So right side up, virtual image that's bigger than the object. Okay, so those are kind of the 3 interesting cases for the concave spherical mirror. But I can also make like a convex spherical mirror. So this would be the kind of spherical mirror you would put up like if you were setting something up to make it easier to back out of a driveway or something like that, and you wanted to be able to see stuff coming from other directions. So in the convex spherical mirror, if I draw a bunch of parallel rays, right, and then I say that they reflect back at the same angle they came in, they all diverge from the same point. So they all diverge from the focal point. So in the concave case, we had a focal point that was on the same side of the mirror as an object. In this case, the focal length is on the opposite side of the mirror. So when I go to draw my ray diagrams, something's going to be a bit different because my focal point is now going to be on the far side of the mirror, and my radius of curvature is going to be on the far side of the mirror. Okay, so the convex mirror problem, we have the focal length of the mirror. We want to sketch a ray diagram for an object at, say, 12 centimeters to start with. We want to figure out all the image properties, right? Upright, inverted, bigger, smaller, real, virtual, and then throw it into our equations to get the image distance and the magnification. So the ray diagram here is going to be actually pretty similar for each of the 2 cases. I'm still going to draw the same 3 rays. So ray number 1 comes in parallel and reflects back through the focal point. But again, through the focal point just means geometrically kind of coming from the focal point. So I'm going to line up a straight edge along the line connecting the focal point and the point where the ray reflects from, and trace that ray outwards. So that's going to be ray number 1. For ray number 2, I need to approach the focal point from the object. So I'm going to line up a straight edge from the object to the focal point, draw that ray to the mirror, and then that ray reflects back parallel. So that's going to be ray number 2. For ray number 3, I'm aiming at the radius of curvature. I reach the mirror, and then I reflect back the way that I came. So again, I've got no real image because these rays never cross anywhere. So that means I'm going to have a virtual image. I can trace those reflected rays back to find the virtual image. And I can see that it's right side up, and it is smaller than the object. So again, with these, it's really important to be careful that the rays you're tracing back are the reflected rays, not the rays that were coming into the mirror in the first place. In terms of using the equations, we have some interesting sign conventions that start to come up here with virtual images. So if I just throw some numbers into the equation, I might notice I start getting negative numbers in my answers, and I have to start thinking about what those negative numbers mean. So the way the equation works out as written is that I will get a positive number for the image distance if it's in front of the mirror, and a negative number for the image distance if it's behind the mirror. The thing that I have to be careful of if I want to get a sensible answer is the focal length needs to follow the same convention. So the focal length needs to be negative if the focal point is behind the mirror, and positive if the focal point is in front of the mirror. So if I am careful about those two sign conventions, I can plug my negative 24 centimeter focal length into the equation. I can plug in my object distance. I can get a negative 8 centimeter image distance, which is fairly sensible, right? We know that the image is behind the mirror and it's between the mirror and the focal point. So 8 centimeters seems pretty reasonable.
So does behind just mean that it is opposite the side upon which light is incident?
Yeah, so the front of the mirror is always the side that light is coming from. Yeah, so typically that would be the object side, and this would be behind. So the behind is the side of the mirror that no light is actually physically passing through.
Got it.
So for magnification, I can plug those numbers back in, and I get a positive 2/3. And that's kind of interesting because there is a negative sign in the magnification equation. And if you include that, then you get a positive magnification if you have an upright image and a negative magnification if you have an inverted image. It's not super important to remember that one, but it's kind of cool that the equation works out that way if you do it the way it's written in the book. Of course, we would already know if the image was upright or inverted from the ray diagrams. This is just kind of a way to confirm that. So if my object's at 12 centimeters, I have a 2/3 magnification. If my object's at 48 centimeters, the ray diagram looks quite similar. I would get an image at negative 16 centimeters and a magnification of 1/3. Okay, so those are the kind of interesting, tricky cases for mirrors. If we want to get into talking about lenses, then we need to figure some stuff out about refraction, specifically the way that light bends when it reaches a medium in which it's going to travel at a different speed. So mirrors make images by reflecting light. The idea is lenses are going to make images by bending light. So as a bit of a review, we looked at the index of refraction for light traveling through water. And right, we had when light passes from a slow medium into a fast medium, the wavelength gets bigger. Right, when it passes from a fast medium to a slow medium, the wavelength gets smaller. So our equation was that the velocity was the speed of light over the index of refraction. We have this idea that the same timing between crests is going to happen regardless of speed, right? When two crests change mediums, the time difference between the two stays the same. So our frequency of the two waves is going to stay the same. So to find the new wavelength in the water, I can look at the new speed with the same frequency and see that the wavelength is indeed shorter, and I end up with 267 nanometers. So what I want to talk about is how does this changing in wavelength from one medium to another mean that light is going to end up bending? So the idea is that if a wave is traveling at a barrier between two materials, let's say in this case that the second material has a larger index of refraction and is therefore slower for the wave, that the wave crest is going to reach that medium and part of the wave is going to slow down while the other part is still moving at full speed. So geometrically, that means that the spacing between these two crests is going to get smaller, which is what we expect. And that means we're going to have this kind of bending action at the boundary. So we can do some trigonometry to get the exact amount of bending that happens. I'm going to look at the angle that the wave is coming in at and call that theta 1. I'm going to look at the angle the wave is coming out at and call that theta 2. Again, these angles are being defined from the normal to the surface, so from this line that's perpendicular to the boundary. And what I want to do is I want to draw some similar triangles and use some trig. So I can start to draw some triangles here, right? These two triangles are nice because they share this side, right? So they have at least one side in common, which is going to be really useful. And the other side of each of these triangles is going to correspond to the wavelength. So they have the same hypotenuse and one of the sides is the wavelength. So I can use some mutual perpendiculars, right? So I can connect this angle to this angle, right? So this, I can take this angle, I can pick it up and turn it 90 degrees to get the other angle. So I know it's the same angle. And so I can write theta 1 and theta 2 inside my similar triangles. And because I know that the hypotenuse of these two triangles is the same, I'm just going to call it L. And then I can use this equation that the sine of each angle is going to be the wavelength over the hypotenuse. And I'm going to solve both sides of this equation for L in order to put them together and get rid of L because I don't actually know what L is. So if I combine those two equations, I get that the wavelength in medium 1 over the sine of theta 1 is equal to the wavelength in medium 2 over the sine of theta 2. If I know the index of refraction, right, I can write each of these wavelengths in terms of the vacuum wavelength divided by the index of refraction, which means the wavelength is going to cancel out, and I'm going to be left with the index of refraction on side 1 times the sine of the incident angle is going to be equal to the index of refraction in the second medium times the sine of that angle. So this is where Snell's law comes from. And the idea is that if a wave is approaching a medium in which it's going to slow down, the wave velocity is going to bend towards that normal. If it's going from slower to a faster, it's going to bend away from that normal. We can arrive at a really interesting phenomenon with Snell's law, which is if I imagine light inside a medium with a high index of refraction, so let's say I have light moving inside glass where I have an index of refraction of 1.8, and that piece of glass is sitting in some air. If my light comes in at a steep enough angle, right, let's say it comes in at an incident angle of 85 degrees, I have N1 equals 1.8, sine of 85 degrees is going to be equal to 1 times sine of theta 2. I end up with this condition where sine of theta 2 is now supposedly bigger than 1. So that's a problem because there's no angle that's actually going to give me sine theta 2 is bigger than 1. So in this case, it's not that the equation has like blown up and now is wrong, but actually that there is no theta 2. There is no light that's actually going to refract through this boundary. In this case, all of the light is going to reflect off the boundary and none of it is going to escape. So this is what we call total internal reflection. And this is relevant for fiber optics, right? If I want to use light to send a signal and I want to send, right, some timed pulses of light or some signal with light through a wire, the way I do that is by having a wire that has a higher index of refraction than its surroundings and sending the light in at a very steep angle relative to that boundary. So in that case, the light will reflect back and forth inside the wire, but none of the energy will actually leave the wire. That's kind of cool. So if I want to figure out like how steep an angle I need to use, I can find the critical angle by saying I want the angle where the reflected ray would have been at 90 degrees. Or a refracted ray at 90 degrees doesn't make much sense. It would be like right along, like perfectly parallel to the boundary, but this would be like the boundary point. If an incident ray is arriving at bigger than the critical angle, then there's total internal reflection. So there were a couple pull everywhere problems about this that were just kind of using Snell's law. The one that's probably the most interesting is there was a problem where it would ask you to find the critical angle for the transition from air into water, right? Where I had some water. And I have, right? So what's the critical angle for this transition? And there is no such angle. I can't trap air. I can't trap the light in the air and keep it from getting into the water. I can only trap light in a higher index of refraction medium. So I can trap it in glass, but I could not trap it in the air and keep it from getting into the glass. I can't do the other way around. So the last of the practice problems for this week looked at basically a prism. And so we were just doing some geometry about Snell's law, and kind of addressing that. One of the things I've already told you is kind of a little white lie, which is the index of refraction. I talk like it's just some number that we know for every single material. In reality, it does have some variation with the wavelength of the light. So in lots of materials, actually different wavelengths of light will experience slightly different indices of refraction. And this is commonly referred to as a diffusion relationship. Wait, no, that's not the right word. I can't think of the right word right now. But you can find these, if you look up indices of refraction for certain materials, you'll actually see a function rather than just a number. So in this case, I'm saying that we have a piece of glass, right? And it has a slightly different index of refraction for red light as it does for blue light. What I'm doing here is I'm actually kind of I'm making up a prism. So if you've ever seen a prism, like maybe back in kindergarten or whatever, you played with prisms where light came in and a rainbow came out the other side of the prism, right? And the reason for that is that red light and blue light will have bent different amounts when they arrived at the first boundary of the glass. And so as a result, the red rays and the blue rays will now be slightly offset from each other in space, meaning I can make a rainbow. So the geometry of the problem kind of looks like this, right? I have red and blue light both coming in at 15 degrees from normal. They are arriving at the boundary, so they're going to slow down and bend towards center. I know the indices of refraction for the red and the blue light in this glass. So I need to figure out the angle. The red light bends to an angle of 9.3 degrees, while the blue light bends to an angle of 8.7 degrees. So I can see that the blue light is not bending as much and is bending closer to center. So the red and the blue light will strike the far side of the prism in slightly different spots. I can figure out the physical distance between those two spots using some trigonometry. So the tangent of the refracted angle will give me the location of the red spot relative to center, over the thickness of the prism. I can do the same thing for the blue light, right? Tangent of that angle gives me the location of the blue light over the thickness of the prism. Take the difference between those two locations, and I can get the physical distance between the red light and the blue light. It is very small. I haven't made a very good prism. If you want to make a nice prism, you would use something like a triangle, because then the light would come in at a really steep angle, plus the actual light rays would end up traveling different distances through the triangle, and so you'd get a really nicely well-defined rainbow coming out the other side. But that does make for a geometrically much trickier problem, so I figured I'd just do it as a slab, even though it makes for a smaller, not as nice prism. Not a great demo for kindergartners. Okay, so that's it for this week. For next time, we will be looking at lenses, right? Specifically, we'll look at how the curvatures of different lenses and the shapes of different lenses lead to different images. And we're going to want to quickly do the same thing we did with mirrors, which is figure out a focal point and then come up with some simple rules for drawing rays so we don't have to actually calculate refracted angles and break out protractors and sketch exact paths through angles. Instead, we want to come up with some tricks like we used for drawing rays in mirrors. Okay, and with that, anyone has any questions, we can talk about those.